I think you can. All right, that's good.
Yes. Can I shortly present you?
Yes, please.
So we are starting our first scientific talk on this hackathon, and our first lecturer is Kyunghyun Cho. Kyunghyun is assistant professor of Department of Computer Science, current Institute of Mathematical Sciences, Center for Data Science, New York University. And so you can read the title of his talk on the screen, A New Territory for Machine Translation. So let's greet Kyunghyun.
Yes, so thanks for the invitation. Well, unfortunately, I couldn't be there, although I really wanted to fly there, but too many things to do here as the semester has started. So today I'm going to talk about the machine translation, but in a sense, not the machine translation that everyone is working on. Rather, I'm going to try to present what are the new opportunities that have been made possible by having a neural net approach to machine translation. So, but before I talk about machine translation, I want to quickly talk about why the natural language understanding or the natural language processing matters for artificial intelligence in general. And the first thing is that, why do we ever bother with natural languages or even the artificial languages at all? And the second question is, has natural language understanding been solved? I thought the answer to the second question would be very clearly no, but there's been some shocking testimonies recently. First, Jan LeCun posted on his Facebook in a comment section saying that well, he's not sure language is as important as we think it is. And I was very shocked. I mean, yeah, no, I came to NYU to the language research, and then you cannot say that language is not important. And then a few days later on, Wojciech Zaremba, who is going to give a talk at this hackathon, I believe, in about 2 days, posted on his Reddit saying that the speech recognition and machine translation between any languages should be fully solvable. And I was like, well, Wojciech, I don't know. I'm working on this thing, and then it's not going to be fully solvable soon. And then furthermore, in 2015, Neil Lawrence, a professor at the University of Sheffield in UK, said during the deep learning workshop panel discussion that the NLP is kind of rabbit in the headlights of the deep learning machine waiting to be flattened, meaning that the NLP is going to be solved soon. And I was sitting in that panel discussion, and I just had to, disagree with Neil. Of course, I didn't say anything to Neil myself, but somehow many people working on machine learning and artificial intelligence these days seems to believe that the natural languages are either solved or it's just one of the problems in AI. But the thing is, natural languages or the languages are a bit different story from the many of the tasks that we work with in machine learning or artificial intelligence. So let's see why it matters in artificial intelligence. So when we think about building an intelligent agent, the agent learns from the environments. And then by the environments, that is the environment that agent can perceive. And often the perception is very direct. If you think about the computer vision, the idea is to make the artificial intelligent agent have the direct perception. So using the vision, using the auditory, or using the haptic sensors to feel what the environment looks like. And then each agent has the history of individual experience, where it knows what has experienced so far, and based on that it can infer, it can actually have a larger perception of the world. But this is very limited. Many of the animals actually do this, but the humans do not learn by the direct perception only. And the language allows us, or allows the intelligent agent to have a distant or collective perception. Because agents can communicate with each other just like humans do, agents can have much larger field of perception, or the horizon of perception. So even without actually experiencing the things, it can hear from the others who have experienced it, and then have the indirect perception of the world. And furthermore, think about learning all those history. And the agents, as a collective society, they can write down their history and then have a much longer historical experience. think about, we humans talk about the Roman history, Greek history, or all those ancient Chinese history. The thing is that nobody has experienced it. Nobody in the earth at the moment have any kind of direct experience or perception of the events happened 3,000 years ago, but we all know. So this kind of historical experience helps a lot. So this is the reason why natural language matters in artificial intelligence. I hope that everyone is going to agree with me eventually. But the question is, why does everyone or the many people have a different view or the different perspective on the natural languages or the role of natural languages in AI from my view? Maybe there is a problem of how we do the natural language understanding or processing with the neural nets or the machine learning. So let's look at how the machine translation these days happens. So let's say we start with some movie review from the IMDb I just took out, and then we're going to try to translate it into French. And then what happens is that first the machine is going to segment the whole paragraph into a sequence of sentences, and each sentence you do the segmentation, tokenization, and a lot of different pre-processing to get a sequence of words. I really enjoyed this film, and period. And that sequence of words finally is fed into the machine translation system, and that machine translation system is going to return a sequence of words, in this case in French. So unfortunately, I don't really speak French, so I'm not sure if that's correct. I just used the Google Translate there. And then once we get a sequence of French words, we do the inverse process or the reverse process of the word segmentation and tokenization we have done earlier for the English sentence. And we often call it de-tokenization, desegmentation, and so on. And then finally, we get a full French sentence. And we're going to put that full French sentence into a translation and then say that the first sentence has been translated. Excuse me. This process happens for the next sentence and a sentence after until the end of the paragraph. When I see this process, when I actually first saw this process about 2.5 years ago, what I felt was that there is something very wrong here. The three issues I saw was that the translation, or even it applies to natural language as well, is that it's a word level, sentence-wise, bilingual translation. And all these three things are problematic. Let me give you a very quick 1-minute intro to neural machine translation. So in this case, neural machine translation tries to tackle this part of the machine translation by replacing the whole thing with a neural net. Oh no, so some of the things are actually breaking down somehow. But in short, what happens with the neural machine translation is that there is a source sentence which is given as a sequence of words or some kind of linguistic symbols. And then the goal is for the neural net to generate a sequence of target linguistic language symbols. And this neural net is trained using a parallel corpus of sentence pairs. So these are the translations generated by either human or some kind of automatic measures. And then we train the model using this data to maximize the log likelihood, which is defined as the sum over all the examples in the parallel corpus, some of the log probability of the correct translation given the source sentence over the whole corpus. And then in order to make it better, we have a so-called attention mechanism or the alignment mechanism that does the implicit and automatic alignment between the two symbols in the source and target. But even in that case, I still see the issues because we replaced the existing machine translation system, but that didn't really include the whole system, right? It was just the mechanism that translates a sequence of source symbols into the sequence of target symbols. So the same three issues, word level, sentence-wise, bilingual, translation, still persists here. So let me go through one issue at a time and then trying to see what is the effort that I'm trying these days to resolve this issue. First one is to go into the subword level. And when I say subword, it's not only about the subword, but all the way down to the sub-characters. So if you look here, what we see is a very clearly, clearly word-level translation. We are given a sentence, and then the sentence is chopped down into a sequence of words, and then that sequence is translated, and then the machine translation system gives us a sequence of words in target language. Not that great, especially if you think about the many languages, except for English and French. Often the languages show very rich morphology, and then it's not even clear how we can define words as they are. I believe Russian also has a similar thing. But unfortunately, I really have no idea about Russian either. So we gotta ask first, why we use words or the tokens. And there is a reason for that. The reason is that it's just easy to get a sequence of words in English and some of the Western languages, because often the words are separated from each other by the blank spaces. So in the case of using Python, all you need to do is just sentence that split and you get the sequence of words. That's great, but there are a lot of issues with word level modeling, right? So for instance, this is Korean word, or like it's difficult to tell whether it's a word or not. Korean word that corresponds to Ministry of Trade, Industry, and Energy. And then it can be segmented into industry, trade, energy, and ministry. So we can clearly see that if we just go for the naive, let's say, word level modeling, the meaning of these 4 words or the 4 subunits need to be represented as a single thing, which is clearly not optimal, because there is a sharing. This word industry can be used by any other words as well. Furthermore, even in English, if you think about, let's say, as an example, run, runner, ran, running, it just doesn't make much sense, at least to me, that all those 3 tokens or the words are considered independent from each other, whereas there is a clear underlying structure that are shared across those 4 words. In this case, this is Chinese. Again, I don't know Chinese too much. I asked my Chinese friend to make up an example for me, and I even forgot what it means. But this is a single sentence. And the very interesting property of Chinese is that there is no blank spaces between words. So somehow we need to automatically segment this out and then turn it into the English-like sequence of words and then do the translation. Furthermore, these days it's all about social media, and then nobody actually cares about typos because people just write it down so quickly and then don't care too much. And the word level modeling just cannot handle this typo, and then you need to have a separate, let's say, pre-processing or post-processing mechanism, which is really not great, considering that I'm working with the deep learning, and one of our mantra is to go for end-to-end learning always. Now the question is, can we use something smaller? So instead of using words, can we actually go all the way down to characters or the sub-characters? And the nice thing is that the neural nets do not ever care about whether the input is words or characters or whatever the type of symbols you're working with. The same neural net can work with the images, same neural net can work with the video, same neural net can work with the, let's say, sequence of characters. Yeah, it doesn't really care how it's represented, and as long as we represent, in the case of natural language processing, represent the input symbol as a one-hot vector, then the neural net is going to just work on it. For instance, if you train a neural net to do the language modeling or translation on the word level model, we see that the neural net learns a similarity at the word level, whereas if you train the same model on the character level, we see that the neural net learns a similarity of characters. So the digits are all here, and some special symbols are there, and then we see that the alphabets are here. But turned out that it's not that easy, because the orthography, or the mapping from the spelling or the sequence of characters to the meaning is very nonlinear, and it's not easy to learn. The example is quite quick, where in terms of the distance in the input spelling space, they are only 1 or 2, let's say, distance away from each other, whereas the meaning is quite different. Furthermore, the computational complexity increases amazingly as essentially the length of the input or the output sequence grows very quickly. In the case of English sentence, on average, each sentence is 23 words long, whereas on average, Each sentence is 115 letters long. So there has been some work in very recent years. Last year, Yoon Kim et al. From NYU and now at Harvard proposed a model to encode a character sequence of each word into a single vector using a convolutional neural net followed by a highway network. So this is great. And similar effort was done by the Ling et al. From CMU, who proposed to replace the convolutional neural net plus the highway net with a recurrent neural nets. Furthermore, from NYU again, Xiang Zhang and others here proposed to not use the word segmentation at all, and then just feed the character sequence as it is to the convolutional neural net. And that effort has been quite constrained to the language model, but very recently, the Wang Ling et al. From CMU proposed to use it in the machine translation, both on the source side and then target side. And then it turned out that it kind of works. So what they did was to separate the word level recurrent neural net and character level recurrent neural net separate. And then every time word level recurrent net makes one advance, you're going to run the character level recurrent neural net to generate the character sequence corresponding to the specific word. But now they are not really satisfying at all, in fact, because they still use the word segmentation. So they do the segmentation first, and then for each word, they run their own network to convert the sequence of characters that correspond to words into its meaning, or the meaning vector. So the question is, can we segment and encode or decode simultaneously, or avoid segmentation in general? It turned out that yes, it is possible. This is the one direction that we are working on. Of course, we are not yet at the level of the other approaches, but it turned out that it is very possible to do that. And then it is possible to build a recurrent neural net that's going to simultaneously segment and generate without the predefined segmentation. The second research direction or the question is that is the character the ultimate level? Well, there was one recent paper saying that no, it is not the ultimate level, but we need to go into the Unicode, and Unicode can be an ultimate level. And I was reading the paper, and I almost got convinced, but because I'm from Korea, I'm from East Asia, we have a different settings for the characters, and I just realized that okay, that is not true, because in Korean, in the case, each character corresponds to a syllable that consists of one consonant, one vowel, and optionally one more consonant. So this is the first character of my first name. And then the thing is that Unicode encodes each and every syllable separately and independently from each other. So weirdly so, in Korean, if we go for the Unicode, we have a much larger vocabulary than if we go for the words. So in this case, we need to go into the even lower level and go into the sub-character level modeling. Turned out that this kind of works as well, but we're still working on it. Hopefully I'll be able to actually get back to you later on with the more results in about a half a year to a year. Now, these are some of the results that I'm getting, preliminary results. So this is on the translation where we try to generate the character level sequence directly, and it's in collaboration with Kyunghyun Cho, who's been working on this recurrent neural net for a few years at University of Montreal. And we see that already the character level modeling, if using our approach, it gets close to the existing word level or the subword level modeling. And in the case of document classification, this is the collaboration with Ijun Xiao at the master student at the Center for Data Science here. It turned out that we can simply just feed in the sequence of characters to the convolutional layer followed by the recurrent layer to do the document classification, and it does as well as the word level modeling. So it seems like it's possible in general. So we'll pass. Now the second issue that we're going to tackle is the fact that this sentence-wise translation. Why is the sentence-wise translation an issue? Let's look at here. Instead of translation, we're going to think of it as a question and answering. At the end of the day, question and answering is very similar to translation, except that the source language is now a question and target language is an answer. Now, let's look at this question. Where did James go after he went to the grocery store? And I'm going to give you answer candidates. First, his deck. Second, his freezer. Third, a fast food restaurant. And the last one is going to be his room. I'm pretty sure nobody sitting in this room can answer this because nobody can tell. There is a huge ambiguity there. And where does that ambiguity or the vagueness come from? Is the fact that there is no context in which the question was asked. It's just simply impossible. But if I give you the context, which is, in this case, which consists of 2 paragraphs, you can answer this so fast without any ambiguity that the James went to a fast food restaurant. And this is from the machine comprehension test corpus. So in other words, context matters a lot, and this is similar in translation as well. In the translation, what can be the context, or when you generate the language, what can be the interesting thing that you can learn from context? You can think of speaker style, or in the case of excuse me, Korean or Japanese, you have the different levels of politeness. Or in other case, it depends on what is the setting, right? The language during the meeting, language that is written, all these have the different, let's say, style or the grammar to follow, and the context can give the model a hint on that. Okay. So in general, if I can say, the context tells us the theme of a document, so that whatever the translation you generate, you're going to get the theme correct. And in practice, that actually corresponds to the model being able to decide better what are the words that are more likely to appear in this document. For instance, you think about doing the language modeling, where we want to predict the following or the intermediate words. So in this case, with a jaw-dropping good turn from the soon-to-be a megastar Vikander, blank is another excellent example of what makes blank. Now there can be a lot of words that can come in there if we don't look at the context. But if you look at the context, we can very easily tell that what is a subset of words that can fit into those blanks much easily. Now in this case, the nice thing about neural net is that the neural net, again, does not care too much about what the inputs are. We can always plug in a lot of different things to a neural net and then train a model to minimize the cost or maximize the objective. And the neural net is going to figure out how best to use or to fuse the input information. So in this case, in the case of language modeling, what we have done is to just give the previous sentences or the information from the previous sentences into the neural net. And we train the model just to do the language modeling, and the neural net figures out how to use the previous sentences to get the better probability estimate of the current sentence. And this was done by one of the master's students at the Center for Data Science again, Tian Wang, and we submitted, this is under review at the ICLR 2016. Unfortunately, I believe this paper is going to be rejected, but the idea itself is still pretty interesting. And in order to do so, it turned out that we can always make a neural net slightly better by making its architecture more suitable for the target task. In the case of larger context language modeling, we modify the long short-term memory units to fuse the information you get from the previous sentences only at the later stage, making sure that the memory cell is going to model intra-sentence dependencies as usual, while this later fusion helps combining the inter-sentence dependency together with the intra-sentence dependence captured by the memory cell. Let me show you some examples. So we tried it on 3 small corpus, and then you see that these dashed lines show the baseline you're going to get with the very basic long short-term memory unit without any context. And this is the number of previous sentences that we let the model take into account. And we see that it gets better and better as the number of context sentences grows. And this is especially clear in the BBC case, where the theme of each news article is very well defined. And if we analyze the model, so this is the part that many people tend to skip these days, is to analyze what the neural net has learned. But if we analyze it, interestingly, the neural net with the context can get the verbs or the nouns or adjectives that are open class words much better than before. And why is this? Because those words can be much more easily spotted or predicted if the theme of the document is known. So let's say if this is a movie review about a certain movie, as long as the language model or translation model knows which movie is talking about, it can much easily predict the word that's going to follow in other sentences because it knows that it's about movie and it's about a specific movie. Now, recently, the Sebastian Zhang, who's a PhD student of mine at NYU, and me, we started work on how to extend this to the larger context machine translation. Turned out that there is slight difficulty compared to a language model because now we have a context both in the source and target, and often in the source side, we have a future context as well. So how to combine them well turned out to be a difficult thing to do. But we are working on it, and we, again, preliminary results show that it's actually helping, even in the case of translation as well. And now, if you think about larger contexts, I've been talking about only the previous sentences, we can actually go all the way to the document. And there are a lot of research challenges. First, how do we efficiently learn and represent larger contexts? And in second, in online setting. So can we build something that's going to read the chapter, it does the summarization, and start reading the second chapter, and inside the second chapter, it's going to read the first section, summarize, and start reading the second section, and then inside the second section, after reading the first paragraph, summarize, and then continue reading onto the second paragraph. Can we build some kind of hierarchical model that does this like automatically? And also, when it comes to training, backpropagation through time is too inefficient because it has to wait all the way to the end and then backpropagate the error all the way to the back. Can we actually avoid that? Those are the research issues that we need to tackle. And then I'm pretty sure many of the people there will be able to tackle that soon enough. I'll just have to move very quickly. Yes. So there has been some work on this direction, especially from the University of Montreal, on how to build a hierarchical recurrent neural net for the dialogue modeling. There is a utterance level recurrent neural net that looks at the single utterance or a sentence, and then that summary of that utterance is going to be modeled by the dialogue level recurrent neural net. Now you can think of this as the paragraph level recurrent neural net, and this as the sentence level recurrent neural net. Now what we want to do is that we want the model to do it automatically, build a topology automatically. And since I believe the goal of this hackathon is to do the Q&A, right? So larger context language processing, in fact, includes that kind of context-dependent or the knowledge-dependent Q&A as well. So this part is the part that I've been talking about now. And in fact, you can always condition your neural net on the word knowledge as well, so that the neural net is not going to only look at the intra-document context, but also look at the whole word knowledge. Of course, there are a lot of questions. How do we efficiently encode word knowledge into vector space? Or how can we do the search over the vast amount of information available in the word knowledge? But this is the direction that a lot of people, including researchers at Facebook and Google DeepMind, are pursuing, yes. Now, lastly, let me talk about the why it's an issue of bilingual translation. So if I look at this translation diagram, it's very specific to a language pair. So this machine translation system is going to read a sentence in one language, and it is going to spit out the translation in a target language, a very specific language. It's not going to be like general, any language translation. And the reason why I'm interested in this kind of multilingual translation is that we actually know quite well, although it's a bit debatable, but in the education community, we actually know that knowing one language often help learning another language. That is why when you see the people who speak multiple languages, they actually have less difficulty learning new language. Meaning that there may be a positive language transfer from the one language to another. But of course, it's an unsolved question, and then one way to solve it is to actually try it out in our case. So in the multilingual neurotranslation is slightly different from the existing translation in a sense that we are now assuming a n source languages and m target languages. And we want a single model that is going to be able to translate from any of the n languages to any of the m target languages. And of course, the biggest assumption here is that we do not have the multi-way parallel corpus. So we do not have a sentence that was translated into m languages in advance by humans, or we do not have the n sentences that have been translated into one by human. And what we want to achieve by doing this is to avoid the quadratic explosion of the number of parameters. So we want the number of parameters to grow only and most linearly. And second, we want the quality of the translation to be as good as the single pair models or better. And third, in the case of low resource language pairs, think about translating from Korean to Russian. It's very low resource language pair. And by putting those two languages into a larger multilingual translation system, we want there to be some kind of positive language transfer that helps having the translation quality better. And the last thing is the faster convergence, and that's what I hope, but so far it doesn't look like it helps with the convergence. Now, in multilingual sequence-to-sequence model, if you do not have attention or alignment model, it's very straightforward. You have an encoder for one language that's going to map the sentence into a vector space that is language agnostic and shared by all the other encoders. And then from the vector, any of the decoder that takes care of each of the target language is going to just spit out the translation. Very straightforward and beautiful. And the number of parameters grows only linearly, and then we get something like interlingual, or the language agnostic sentence vector that contains the semantics but without syntax. But the issue is that we all know that the neural machine translation works best with the attention mechanism. And then Luong et al. From Stanford uploaded this paper on arXiv recently for the iClear 2016. And then, while reading the paper, I had to just keep asking the question of why can we actually have the attention mechanism there? And the big question there is that is the attention mechanism universal or language pair specific? So in fact, even before this Luong et al. Paper, with one of my collaborators, Orhan Firat, we were working on making this attention mechanism to be shared across multiple languages. And it took about a year for us to get it right. But it turned out that the preliminary answer is yes. So we built a neural machine translation system that works with any of the languages while sharing a single attention mechanism. So in other words, a single attention mechanism we have in the model can align between any pair of languages. So this is the Orhan Firat, who's my collaborator, who's at IBM at the moment. So we decided to empirically verify it by having an English encoder, German encoder, and Finnish encoder, an English decoder, German decoder, and there's going to be a single shared attention mechanism. In fact, we even went further to include 5 languages to 5 languages. English, French, German, Czech, Finnish, to English, French, German, Czech, Finnish. And then it turned out that we can train the same model, and single model, and it works as well as 5 or the 10 different single pair language models. Well, there were some differences, but in general, they were very comparable. And then in that case, because the number of the parameters grows only linearly, we were able to save a lot on the number of parameters. Furthermore, it turned out that this kind of multilingual approach really helps for low resource language pairs. So we made some artificial low resource language pair by using a smaller, only a subset of the parallel corpus. And in that case, the multilingual model always worked better than the single pair model or single pair model with the monolingual corpus added. Now the interesting thing about this multilinguality is that we can push it a bit further and make it into the multimodal and multitask learning. For instance, instead of having a language encoders, we're going to put the image encoder. And we have had some success with the image caption generation, and that makes me wonder, why not? Let's just plug in the image encoder there, and then the attention mechanism, that shared attention mechanism, to work also with the images. And think about putting in the speech encoder. And then even in the decoder case, we're going to put the image decoder, speech decoder, and then all the other languages. Then can we actually get a single model that is able to handle any kind of modalities to generate any other type of modalities? So that's going to be a big future question. Now, what I have done, so let's summarize now, is that the neural machine translation or the natural language processing with the neural net, this research is going beyond the usual word level, sentence-wise, bilingual or the monolingual, let's say, processing. We are now at the point where we can push on to the subword level, larger context, multilingual, translation, or understanding. So I hope this message has been, let's say, delivered very clearly. And now, interestingly, all these things, let's say, multilinguality, character level processing, and larger context language processing, all tells us that in fact the natural language processing or machine translation is now making its comeback as a very nice testbed for artificial intelligence in general. So let's look at this. Multilinguality corresponds to the multimodal perception of the artificial intelligent agent. And direct perception corresponds to, okay, going all the way to the character level. So do not assume anything about the representation of the language, but let's go into the character level directly. It's just like what happened with the speech or images. In the case of computer vision, these deep convolutional neural nets have made it possible for us to work at the pixel level, and we get better results because we do not assume too much. And I believe same thing is happening with the languages, and that is kind of prerequisite for the artificial intelligence. And larger context tells us that corresponds to the long-term environment understanding as well as knowledge accumulation and search. So if we can get this larger context language processing or the language understanding correct, we are one step closer to having an artificial intelligent agent that can understand the environments much better and also go through the knowledge base much better. And there are a few other things that are still is a bit vague, such as can we actually have a natural language agent that can do the research, event detection, and retrieval, or doing the navigation. This is the future work that I'm working on, and I'm pretty sure many of the speakers later on will talk about. So when I wrote the lecture notes, Stanford NLP group tweeted saying that the path from neural language models through neural machine translation is rather one-dimensional, not really the natural language understanding. But I hope that it's clear now that going through the neural machine translation and further, in fact, gets us to the natural language understanding. So this is the final slide of my talk, and if there's any questions or the comments, I'll be glad to stay and answer.
So questions, please. Can you hear us?
Yes, yes.
Thank you for the lecture, and my question is about processing of large pieces of text in a hierarchical way. What do you think about these dynamic memory networks? Are they doing, how do you place this work in this picture? So they are basically getting one vector representation for each sentence, then have another RNN working on sentence level. Is it something that you fit in this picture?
Yes, yes. So let me go back one slide. So what happens is that currently, yes, dynamic memory nets or the just usual memory nets, neural Turing machines, all those things that you can think of are saving the previous sentences into a memory slot. And then so far, what has happened is that there hasn't been much work on how to put this structure or the hierarchical structure in the memory. The memory has been rather flat. So they've put all the sentences, each of them as a separate vectors into the memory, and the recurrent neural net or the controller is going to do the accessing over that. Whereas what I believe needs to be happen is for the neural net or the memory structure to have this kind of hierarchy. So we are going to have a summary of the chapter, as well as a summary of the section, and summary of the paragraph, and then sentence vectors. And now the question is, how can we get that kind of hierarchy automatically by looking at a much longer documents, and then to do the efficient search over that. In other words, you can think of building a tree as a memory, and then we're going to put at each node a set vectors that summarizes the subtrees or the nodes, subnodes, and then doing the, let's say, indexing, addressing, or the retrieval on that. So I believe we are on the way to go, but I don't think anyone has done a great job at doing it yet.
Thank you. So you mean that the hierarchy introduced in these memory networks are kind of hard-coded. They are not learned by the network itself, right? So
right. We don't have. We still don't have any kind of hierarchy yet. Many of the works, they never actually consider the hierarchy too explicitly.
Okay, I see. So maybe just 2 levels is not enough, right?
Right, right. That's how I feel. Because if you think about how you view it, let's say think about going to the library. We start with the library, and then there is a sections, right, floors. And then inside the section, there is a different authors or the themes. And then you go there, and then you go to, let's say, one of the authors. There are like books by that author. You choose one of the books. There is a chapters and sections. So there is like the infinite levels of hierarchy. And then, we haven't really exploited it well enough. And that's going to be probably the next thing that many people are working on.
Okay, thank you very much.
Next question, please.
Thank you for the lecture. Can you please explain one more time the intuition behind the idea that splitting the text into smaller and smaller pieces helps with the language processing, and doesn't it diverge with the idea of larger contexts?
Oh, yes, okay, let me try to go to the character level. So the reason why we want to go below word level is that the words, there are a lot of different reasons. First of all, the words are not well defined. Words are not well defined in many languages. So in this case, for instance, let me see, where did it go? Yes, in this case, this is one word in Korean. If you think about the word as a the unit in a sentence that is separated by the blank spaces, this is one word. But at the same time, this is one word, this is one word, this is one word. And that they do not correspond well to the words in English as well. So in a sense, the using words is kind of artifact from the fact that we were not able to handle a very long sequence of characters in the existing approaches. But now with the neural nets, it's not true. We can actually use the either words or characters without any problem. So that is the reason why I think we need to go in that direction. And the nice analogy is to the computer vision, object recognition. So before 2012, when the Jeff Hinton, Alex Krzyzewski, and Ilya Sutskever showed that we can actually build a deep convolutional neural net that's going to work at the pixel intensity level and still does the even better job at the existing approach. That's just like the character level modeling. Whereas the previous ones, where they used all those feature detectors, feature extractors, and then feature vector to get some kind of artificial thing, corresponds to word level. So we are actually now just catching up with the computer vision research, or how the neural net changes the computer vision completely. So that's one thing. And then there is no reason why it doesn't really map, let's say, it's not compatible with the larger context, because the context can be represented in a sequence of characters or sub-characters as well. So we can use the character level thing both for the current sentence or the current task, as well as to represent the larger context or the previous sentences. I hope that answers the question.
So the next question.
Hello, thank you for the great lecture. I wanted to ask you about what do you think about the problems when we have a lot of prior information about maybe concepts and relationships between them. I mean, this approach seems to be a bit naive about physical world and stuff that will goes on there. And I mean that conceptual space can be pretty much, I don't know, it can be in any shape just to just be able to accept the constraints that decoders and encoders and attention mechanisms have. But what about maybe situations when we want to have implicit relationship learning or something like that?
Mm-hmm. Okay, so implicit, so relationship, yes. So I mean, like if we have some kind of prior, let's say we have a very clear prior about what are the relationship between the entities or the, let's say, words in the sentence or across the larger context we have. The idea is that the nice thing about neural net is that we can always enforce or encourage model with the existing prior knowledge. Let's take an example as the attention mechanism. Let's say we know certain correspondence between the, let's say, source phrase and the target words. Then what we can do is that when we train the model, we can put as a regularization term that's going to force the attention mechanism to align those two things explicitly, very explicitly. So in a sense, whatever I talked about, or whatever many of the neural net researchers are talking about, do not really say that we are going to, let's say, ignore all the existing prior knowledge. In fact, this kind of neural net approach is better at incorporating those prior knowledges because it's a nonlinear model with a very flexible structure. And then next thing is, so can these neural nets learn those, let's say, implicit relationship in the word level, let's say, in the word knowledge? That is a big question. And then, of course, if you believe that how humans have learned all those relationships among the entities in the word is via learning by observation or the hearing from others, then if you train a model with all those knowledge that has been accumulated over time, the model should be able to capture that. That's how I believe it. Of course, that does not mean that we can do it now, because the set of tasks that we consider, the objectives that consider, do not necessarily overlap completely with what the humans have as their objective for the tasks. But eventually, if we actually push further so that the neural nets are trained to do what the humans are doing, like let's say all of them, then the relationship will automatically emerge by looking at the data to learn to do all those objectives and tasks. That's how I believe so. But we'll see in about 5 to 10 years.
Okay, more questions?
So in order to use deep learning models, we need a lot of labeled data. So in the case of machine translation, we need a lot of translated sentence pairs. But can we use unsupervised learning to make neural machine translation better?
Yes, that's a good point, because I really so like recently Yoshua Benjo and Jan LeCun, they are going crazy about like promoting unsupervised learning. But I ask myself, what is like unsupervised learning? In a sense, what I think is that I'm more on the side of the multitask learning, where the number of tasks goes to infinity, essentially. And then clearly unsupervised learning is going to be included in that. And if you think about the multilingual translation example I said, is that we do not have to have a large set of label set for every single objective or the tasks that we have. What we want is that we want to have, let's say, a lot of tasks where in each task there are a small set of labeled tasks, labeled examples. But if we combine them all, then we get a large set of labeled examples. So in the case in the slide, what I'm showing is that the low resource language translation, in a sense that it has a very small number of labeled examples, but by getting help from the other tasks, so for instance, tasks with the more labeled examples or the many tasks with a small number of labeled examples, we can actually get better. Because at the end of the day, what you want is your model to capture the underlying structure. And then to capture the underlying structure, it doesn't matter whether it's unsupervised or the supervised, but the important thing is to have the model to have access to as much data as possible. That includes not only the unsupervised learning, but also trying to do the multitask learning with the many tasks that have small amount of label examples. So in the case of translation more specifically, I think by going into the extreme multilingual translation, we might be able to get around the issue with the lack of bilingual corpus largely. I hope that helps, that answers. It's just one way to go, yes.
Thank you. More questions? Yes, please.
Hi, thank you for the interesting talk. My question is that, as I'm seeing from the slides, your multi-language translation is working only with the European languages now. Is there some fundamental issue with Asian languages, or is this just the example? Thank you.
Yeah, that's a good point, especially the fact that I am actually from East Asia, so I should work on that. But there are a few issues. One issue is that except for Chinese, when it comes to Korean and Japanese, there is just no data. So what happened to Japanese English parallel corpus and Korean English parallel corpus is that those parallel corpora are kept by companies, and they are very unwilling to share that kind of data with any other entity, including academia. So that is actually one reason why we haven't really worked with the East Asian languages too much. And for this paper, the reason why we went there was to just use the existing data from WMT. And then if you look at the language there, French, Czech, German, Russian, and Finnish, they are from the WMT 2015 challenge. But of course, there is no reason why we cannot go into the Chinese or Korean or Japanese. In fact, that is one direction that we are pursuing. But there is one very big thing that needs to be solved first, is the subword level modeling. If you think about Korean, because I showed some examples in Korean, word level modeling or even character level modeling doesn't make much sense. And in Japanese, similar thing. In Chinese, similar as well. In fact, one of the students, a master student who's working with me at the Center for Data Science, he is working on trying out the sub-character level processing of the Chinese in order to do the document level classification. And it seems like that is much more efficient both in computation and in memory. So those kind of work will need to be done first in order for us to include more Asian or the languages that do not use the Latino alphabets.
Thank you. Thank you. More questions? More questions?
Can you give us some hints on using ontologies?
Mm-hmm. Yes, so that's true. So let's not even talk about ontology, but think about any kind of structures that we as humans have found over, let's say, I don't know, a few thousands of years. So the idea is how we can use that kind of existing knowledge, or how to make a neural net to use that kind of existing knowledge. And then there are many different answers, and everyone probably has different answers, but my answer is to let the neural net decide. And how do we do that? Is by giving the neural net some kind of access mechanism, which can be, like thought as the attention mechanism or alignment mechanism. And when you look at the translation, the most exciting thing that I found was that this attention mechanism was able to spot from the source sentence or the source knowledge set that is relevant for the current task. So you can think of adding all those, let's say, ontology or any kind of knowledge we have into a database, and then neural net is going to access the database. In fact, for instance, quite a recent work on the reinforcement learning recurrent neural Turing machine, essentially that paper was saying that we can train a model to use to make a neural net to use the database, where in the database there is an interface of, let's say, access certain address or the take it out or the override. And then if we can train that kind of model using any kind of knowledge we have with some kind of hierarchical structure in the memory, then we can use any kind of existing approach. But of course, it's a too high level answer, right? But hopefully this is the general direction that I think should be done. But everyone has their own opinion, so I cannot really talk on behalf of everyone else.
One more question. Thank you for presentation, and I have several questions, 2 questions. First, what is the size of the layer in your task? What the size of you typically use? I mean, in RNN or
right. Right. It actually differs for every task, but let's go for the multilingual thing. So that's where we had to actually decide on a lot of, let's say, the sizes of a lot of layers. So in this case, actually what we did was to simply go for the same number of units per layer, and then we chose 1024 for every layer. So in the encoder, there were 2 layers because it's a bidirectional recurrent neural net, each having 1024 hidden units of GRU. And then in the decoder, we had, again, for each decoder, 1024 GRU units. And in the attention mechanism, we're using, again, 1024 hyperbolic tangent layers. So often we don't, well, my work has been quite constrained by the amount of memory on GPU and the availability of computing resource. But one thing I have noticed is that the larger the model is better, but often if you come up with a smarter, let's say, architecture that fits your target task well, it gives you a more boost than just having a larger model. Does that answer your question?
Yes, yes. It's quite aligned with our results. You mentioned the paper from Yoon Kim.
Yes.
And we also tried. Have you heard about the CharRNN article from Andrei Karpathy?
Oh yes, yes.
Yeah, we tried his model with some little modification and use 2 layers of 4096 cells, and got preliminary results on Russian with a much lower perplexity than in this paper from Yoon Kim.
I see.
So we were quite surprised and trying to compare these results.
Right.
And the second question is about the architecture of cells and neural nets. How do you think, is it enough to play with these architectures to make a neural net and is able to understand, some logic? For example, if I ask a neural net about something and it decided to ask me again to give me more information. So is it enough to play with these layers or cells or etc., or we have to use some different approach like reinforcement learning or neural Turing machine you mentioned?
Yes, that's actually a super good point. And if you, let me see, so okay. So that corresponds to active discovery, learning, and planning. And unfortunately, I don't think we have a very nice evaluation or benchmark task for that. So that's probably why we haven't had much, let's say, progress in recent progress in, let's say, active discovery, learning, and planning in terms of the natural languages or logic. I believe what we have now is going to give us something as long as we get a benchmark task there and then test it. But as I said, it's all about memory. So the issue with the current recurrent neural net is that it has a finite amount of memory. And what we want is that if we want our model to gather the information, there has to be a much more efficient way to save what has been discovered as it is to the memory. So for that, we probably need to work on more on the architecture side, where we get the better way of incorporating the memory or the external memory device into the neural net. But at the same time, most of the learning criterion we use is very much focused on getting things done in let's say one pass. Whereas now when it comes to active discovery, we need to excuse me, we need to have some kind of hierarchical goals. So we'll have to come up with a case where the agent is not only learning by achieving the final objective, but needs to learn as it attempts to get to the final objective, which requires us to give some kind of hierarchical reward and then updating the model on the fly in an online manner. In other words, we need some kind of new or the radically different learning objective that we use. But of course, what that is going to be is difficult to tell. But so my suggestion always is to actually build a benchmark task first, which I'm working on as well. And then once the benchmark that is sufficiently difficult and then has a sufficient levels of difficulty, then we'll be able to make a much faster progress, just as the machine learning or the object recognition has done so far.
Thank you. Do we have more questions? No. So, Kyunghyun, thank you very much for your great talk, and I think that everybody liked it, and we have a lot of questions. And thank you for participating in our event and for your collaboration.
And thanks for the invitation. I really enjoyed it. The questions were really great. Yes.
Okay, let's thank Kyunghyun.
Thank you.
Okay, thank you.
All right, enjoy your hackathon, guys. Bye-bye.